So the next talk here is Copy on Pin by David Hildenbrand. He's a PhD student at TU Munich, and he's also an engineer at Red Hat, so that's actually a good thing. He's working as well as doing a PhD on the side, so it needs a lot of encouragement.
Yeah, I like to torture myself. So hi everybody, I'm David. I'm a PhD student at TU Munich, and to feed the family I work at Red Hat. In this session I want to talk about our paper called Copy and Pin, the missing piece for copy and write, that has been co-authored by Martin Schulz, also from the TU Munich, and Nadav Amit from VMware Research. So in our work, we took a look at the interactions between two common and important memory management features. On the one hand, copy and write, on the other hand, page pinning. Copy and write is primarily used to save memory, but also to speed up certain memory management operations like taking memory snapshots. And page pinning is primarily used to improve performance, but also to simplify operating system design. Now, what we can see is that both features are getting more important and more widely used, also in combination, and the issue here is that there are problematic interactions in operating systems when we end up combining both features. Now, to understand a little bit what these problematic interactions actually are, let's take a look at some background. So what is copy and write? Copy and write is heavily used for memory deduplication, fast process cloning using fork system style system calls, and much more. In all of these use cases, what we want to do is we either want to defer duplicating a page or we want to deduplicate identical pages. In any case here, instead of using multiple physical pages, we want to use a single physical page and map that single physical page read-only into our page tables. So as soon as one of these, let's assume process page tables that maps such a shared page read-only wants to write to that page, we have to handle a write fault that we get and perform certain action. And what we don't want to do is we don't want to end up modifying a page that is still shared, because that would violate the desired semantics of copy and write. Now, assume that we have one process page table mapping a page read-only and we get such a write fault, we have to make a decision. Do we always simply want to perform a copy, which is fine because we can map the copy read-writable, we can write to that page, and we most surely won't affect anybody else that might be sharing that page with us. Or alternatively, if we're pretty sure that nobody else is sharing that page, we might just be able to reuse that page and of course avoid a page copy. Now, what is page pinning? Page pinning is a little bit harder to get, I would say. It's a mechanism that's used to efficiently access process memory, either by the operating system or by I/O devices when they want to perform direct memory access to process memory. Page pinning can be thought of a form of address translation, whereby our input is a virtual address in our specific process, and the output is a virtual address in our virtual address space of the operating system, and that is in the part of the direct mapping. The direct mapping is essentially a one-to-one mapping of all physical memory into our virtual address space of the operating system. So assuming we have a page mapped into our process page table and we want to pin it, we're going to look up which physical page is mapped there. We're going to use that alias in the direct mapping, so from that point on we would be pinning that page, and the operating system has to make sure that in most cases that we always end up having both of these mappings point at the same page. Because otherwise an I/O device that might be using the pinning reference might end up modifying or reading a page that is no longer in our process page tables. The main takeaway here is that process page table, we can remap page table, for example, page migration, copy and write, whatsoever, but our direct mapping is fixed, so we cannot remap that. And is that an issue? It surely is if we might end up remapping what's mapped into our process page table and we still have that page pinned at the same time. Now, in our paper we cover a lot of problematic interactions. I'm only going to share one example here. So let's just assume that we have a page mapped into our process page table, read-only, and we have the page pinned, and now we get a write fault. Of course, what we might end up doing is we might decide, oh yeah, this page might be shared, so we're simply going to copy it. And at that point, we exactly have that issue that our I/O device might be using a different page that's actually mapped into our process page table. So in this specific case here, we could end up with stale data, reading stale data, writing stale data. And in this particular case, we really must reuse the page. And this is like when you realize when we combine both features, suddenly if we copy or reuse a page ends up in more correctness issues, and we have to be very careful what we do. Now, motivating a bit like why this is important, the thing is, what we saw is that these problematic interactions, they repeatedly resulted in stable versions of operating systems in memory corruptions, security vulnerabilities, and performance degradations. And this has been shown to be a recurring problem. Some of these bugs that were found 20 years ago, for example, in Linux more than 20 years ago. They affected multiple operating systems, and throughout our research, we found new cases in Linux, FreeBSD, and NetBSD. So our claim is that these interactions were actually not well understood and also not well defined. And of course, that's where we take over. Now, if we want to understand like what these problematic interactions are and how to actually get the correct solution to the problem, we first consider the possible states of our physical pages in the system. They might be pinned, they might be shared, they might be neither pinned nor shared, and they might be pinned and shared. And to handle copy and write and page pinning, we have to make certain decisions. So do we want to share a page that's already pinned? Do we want to pin a page that's already shared? And in all of these cases, do we want to reuse or copy, or do we have to copy, or do we have to reuse? And as it turns out, if you have pages that are both pinned and shared at the same time, you're in trouble. As we explain in our paper, there are scenarios that are very expensive to solve. So if you would get a copy and write event and to resolve that could be very expensive. But there are even cases that are impossible to resolve. And that's, of course, an issue if you want to achieve correctness. So can we simplify? Yes, we can. This is the copy and pin scheme that we describe in our paper, where we essentially avoid that problematic case whereby a page is both pinned and shared at the same time. And then it actually gets pretty easy, I would say. So assuming we have a page that's shared, we simply won't allow to pin it. We will still allow to share it. And in any case, we have to copy. We will never allow to reuse that page, essentially. However, if you take a look at this picture now, we have to clearly identify pages that are pinned and pages that are shared. So we have certain tracking requirements per physical page. For example, we have to track the number of page pinnings to identify reliably if a page is pinned, and the same for if a page is shared. However, as history has shown, this precise tracking that is required is rather hard. On one hand, it's error-prone, and that's also been shown in history. We might require more metadata per physical page to actually perform this tracking, so to have some space to perform this tracking. And we might require expensive synchronization, which we want to avoid. So again, the question, can we further simplify and maybe optimize the whole approach? And this is then what we propose in our paper. It's called a relaxed copy and pin, which is based on the copy and pin scheme. What we realized is that we can simply consider more pages as pinned and more pages as shared without harming correctness. And the question is then, like, how do you actually define or make a decision if a page might be possibly be pinned or possibly be shared? And in fact, we then have many possible solutions how to design that, because it's just like a matter of defining primitives. And in any case, it ends up being a trade-off between simplicity and robustness and unnecessary page copies. So assuming, for example, that we consider too many pages as pinned, we might not have as many sharing opportunities and the other way around. So in our design in Linux, we were fortunate that there was already a primitive to detect if a page might be pinned. I'm not going to go into details, but it's based on some advanced reuse of the page reference count that already exists. And what we added is a mechanism to detect if a page might be possibly shared. And for that, we use a single page flag per physical page that is able to clearly express if a page is certainly exclusive or if it might be shared. Now, we implemented our design in Linux, and we evaluated it, of course, and I don't have time to go too much into the evaluation here. I'm only going to share one experiment and one result. But in general, we compared our approach with the two prior schemes of handling copy and write and page pinning in Linux. On the one hand, the approach that was used until Linux 5.8, which implemented some kind of precise copy on pin where you precisely want to identify if a page is shared or not. And that approach was abandoned because of not correctness issues, because of complexity concerns and some bugs that were hard to resolve. And the other approach we compare with is the implementation that was used after that one, starting with Linux 5.9. And because it doesn't implement copy and pin, it had known correctness issues that we essentially resolved. So in this experiment, what we end up doing is we run a modified stream benchmark and we measure, on the one hand, the memory bandwidth, on the other hand, the number of page copies during copy and write events. And what we do in this experiment is, before each iteration of the stream benchmark, we trigger certain actions that end up mapping a page read-only into our page table. So whenever we access the page, then during the stream benchmark and we write to it, we get a write fault, and we have to make a decision if we want to copy or reuse. And of course, memory bandwidth, higher the better, as always, and page copies, lower the better, because in this test case, or this specific experiment, any page copy is unnecessary. So if we end up with 0, it's perfect. If we end up with more, that means, yeah, there might be a problem. And just to summarize, what we can see is that our approach turns out to be at least as good in common scenarios, which is very nice. But it only creates unnecessary page copies in corner cases that we're not really interested in. So to conclude, in our paper, we took a look at the interactions between copy and write and page pinning, and we concluded that the interactions are now not well understood and not well defined. We described the copy and pin scheme, which is an extension of the well-known copy and write scheme, and it is able to achieve correctness by avoiding these problematic cases. Our relaxed copy and pin design is able to achieve correctness without memory and performance overheads and by avoiding complexity. And it was already integrated into upstream Linux, so in case you run Linux on your notebook, could be you're running that code already. And last but not least, I'm going to raise one research question. Page pinning can be considered some form of a necessary evil until now because it's required to achieve simplicity in operating system design and performance. Question is if there is a performant alternative, and so we are able to avoid page pinning completely. That's it for my talk. Of course, for more details, feel free to read the papers, stop by the poster session, or ask a question just now. Thanks a lot for your time.